Suppose that we have a 2-qubit register. How can we describe its joint state? Well, in the same way that the state of a qubit register is in a superposition of the two levels of the system, 0 and 1, it turns out that the state of 2-qubit registers is a superposition of all possible combinations of the first qubit register being 0 or 1 and the second register being 0 or 1. So, the general state of 2 qubits can be written as a linear combination not of 2 but of 4 states, which in the computational basis of 2 qubits will simply be 0, 0, 0, 1, 1, 0, and 1, 1. So similarly as before, we have a complex valued vector to represent the state. The vector just consists of the vector of probability amplitudes. So this means that a priori we need 8 real coefficients to identify the state. However, similar to the 1-qubit case, there are a set of constraints that these vectors need to verify. First, the state must be properly normalized, meaning that the sum of the magnitude squares must add up to 1. And just like in the case of a 1-qubit universe, in a 2-qubit universe, the global phase of the 2-qubit system is not relevant. Okay, so that means that the full description of a 2-qubit state requires us to specify 6 real valued parameters. It's going quite fast, from 1 qubit to 2 qubits. So this may hint at a problem which we will discuss in a moment. In any case, before we move any further, you might be wondering if we will discuss a Bloch sphere for 2 qubits. Well, it turns out that unfortunately there is not really a convenient graphical representation for more than 1 qubit. So we will not go into that direction. Before we proceed, I will introduce an operation, the tensor product. For our purposes, I will only define it operationally. Given 2 matrices, in this example vectors, the tensor product between them is the matrix that results by creating a block matrix with 1 block per entry in the first matrix, and each block consists of the corresponding element of the first matrix times the second matrix. Well, this is quite of a mouthful, so we can see here an example with 2 vectors, phi and psi. In order to obtain phi tensor psi, what we do is to create a block matrix with 2 entries. The first one consists of the first entry of phi, which is A0 times psi, and the second one of A1 times psi. So the tensor product is an operation that will be very useful for defining the states and gates of multi-qubit systems. Similar to the 1-qubit case, we are free to choose the basis of our 2-qubit space. Similar to what I did previously, one can construct a basis for the 2-qubit space by combining an orthonormal basis from each qubit space. The state of the 2-qubit system will be given then by the superposition of all possible combinations of the 2 bases. The operations that take us to the appropriate vector representation is the tensor product. If we work it out, for example, for the computational basis of the 2 1-qubit spaces, we see that indeed we recover the vector that I gave earlier in the definition. Similarly, we could define the basis as the combination of the plus-minus bases or any other combination. Alternatively, one can also directly give a base of the four-dimensional complex vector space, we could say that we will define a four-dimensional quantum system that will be in the superposition of all combinations of 2-bit strings, that is 0, 0, 0, 1, 1, 0, and 1, 1, and identify each string with the corresponding element of the canonical basis of dimension 4. This gives us again the same vector as before. For this reason, we identify ket0 tensor ket0 with ket0, 0. One final piece of notation to avoid clutter. We will sometimes drop the tensor product and just write ket0, ket0 instead of ket0 tensor ket0. Now, we have defined the state of a 1 and a 2-qubit registers. You can imagine if I give you a 3-qubit system, then the general state can be written as a linear combination of 0, 0, 0, 0, 0, right, all the way up to 1, 1, 1. That is a linear combination of 8 states for an 8-dimensional complex vector space. So, in general, if I have an n-qubit register, it will be in a superposition of the 2 to the n possible combinations of the n-qubit registers, always with the restriction that the sum of the probability amplitudes squared is equal to 1. So let's say I give you a register of n qubits. So how many real-valued coefficients must I specify to fully determine the state? Please pause the video a moment and think about this. For 1 qubit, we needed only 2 values, which allowed us to represent state as points on a sphere. For 2 qubits, we had 6. In general, since we can ignore a global phase, we can take the first coefficient to be real. Then we also have the normalization condition, which means that once all complex coefficients are chosen, the real coefficient is also fixed such that the norm is 1. So we have 2 to the n complex coefficients to start with. That means 2 times 2 to the n real coefficients. But, as we discussed, we can remove one to account for the global phase, and a second one for the normalization. So this leaves 2 times 2 to the n minus 2 real coefficients to specify the state of an n-qubit register. The number of coefficients grows exponentially with the number of qubits. This is hard to picture, but we can get an idea by thinking that even the most powerful supercomputer would not be able to store the state of an arbitrary quantum register of 200 qubits. While we typically talk about n-qubit registers, sometimes it is more interesting to consider an big N dimensional quantum register that can be in a superposition of big N different orthogonal states. To avoid confusion, we will use little n to denote the total number of qubits and big N to denote the total dimension of the system.